So, and just heads up, does the camera interfere with everybody's view of the board? So as a reminder, we have an independent study course, and so I want to post these lectures for them as well so they have access to them. So we'll typically be recording the lectures. So chapter 1, they kind of introduce the concept of forces, what a force is, how we use them, how we analyze them, okay? And so I know that it's not the most exciting material that you've come across in your time at Dunwoody, but it is a necessary evil, and it kind of sets the groundwork for where we're going to go throughout the semester, okay? So, the thing I should ask too, the terminology quiz, did anybody have any issue? I forgot to look at it here just before we got going. I looked at it about half an hour ago. Anybody have any issue finishing it? Okay.
I don't have my book yet, so.
You don't have your book yet? Okay.
No, I'm waiting on Amazon.
Okay. When are you going to have it?
Friday. I think Friday, yeah.
Okay.
Same day as him.
Okay. So I'll open it up until midnight tomorrow night.
Oh, I got it done.
Oh, you're done with it?
I just borrowed Steve's book.
Okay.
Oh, I'll just do that too then.
Okay. I'll open it up for you. It's technically closed now, Justin, but I'll open it up through the end of the day for you to finish it up. Or if you want until the end of Friday, let me know. So. Okay, so it has a bunch of sections. We've got some terminology that we'll address, and then we'll look at a couple example problems that'll lead right into the homework, and it'll lead into the lab. Right now, I know it's just a pile of boards, but I'll get it sorted out before we get going on it next week anyway. So the first section talks about properties of forces. And one of the things that you had in your terminology was to define a force. So what do we know about what a force is? What is it?
Mass times acceleration.
Its equation is mass times acceleration. Yep. And how do forces impact objects? How do forces impact structures? What are they trying to do?
It tries to change the motion.
It tries to change its motion or change its shape. Okay, so it's trying to deform or move our structure. Okay? One of the things that we should think about is typically when we're thinking about construction, what do we want the rate of our acceleration to be?
Nothing.
Hopefully it's 0, right? Because what happens if we have an acceleration greater than 0? It's moving, right? So if we're pouring a concrete wall, and after we get done pouring it, we remove the forms, and that wall has acceleration, it's not staying where we want it to, okay? So yeah, generally speaking, and that's where the statics portion of the description of this course comes from. We want to get to static equilibrium. We'll talk about that in a second, okay? So, but think about some of the forces. So one of the forces it talks about in the book is our weight, right? So our weight is our body mass multiplied by the speed of gravity. Okay, that's why we weigh more here on Earth than we do on the moon. Earth has greater gravity, but what are some of the forces that you'd interact with out in the field? What are some things that you could think of?
Wind.
What's that?
Wind.
You could have wind loads. Dead loads, yep.
Live loads.
And I know we talked about all of this stuff last semester too, and what's the difference between our dead loads and our live loads?
Dead loads is structure, live loads is occupancy.
Yep, dead loads is going to be our structures, okay? So these are things that they're always going to be there, right? They're always going to be impacting our structure. Our live loads, or you may also hear them as transient loads, may change over time, okay? So this will be things like, and I remember we talked about it last semester, maybe you remember, maybe you don't. Typically speaking, office furniture is going to fall into the category of live loads because we can change our arrangements of our offices, we can change the arrangements of our interior. When we're dealing with things like HVAC, that typically will fall into dead loads, okay? So those are things that kind of once they're put into place, they're staying there, okay?
Roof loads.
Roof loads, yep. Okay.
Snow loads.
Snow, yep.
What's one to do with earthquakes?
Earthquakes.
Yep, earthquake, hopefully while we're in Minnesota, we aren't dealing with that too much, but some of you may go on to do work where you're traveling around the country, and this does create issues for us, and designers have to account for it. Okay, so you'll see increased reinforcement. We'll look at increased lateral resistance in our structure. Okay? What about the other two kind of basic forces that we talked about? How we actually act on members. What are we talking about when we're trying to pull something apart? Do you remember? What system? What are we putting the system into?
Tension.
Tension. Yep. So our tension forces are when we're trying to pull systems apart from each other. What's the opposite of it?
Compression.
Compression. Okay. So generally speaking, everything that we're going to deal with is going to be generated from these tensile and compressive forces. Depending on how they're actually acting on different areas, we're going to get into things that we'll talk about this semester, things like shear, things like buckling, and things like torsion. Okay, so where we're compressing and rotating. So they also talk about the difference between a vector and a scalar quantity. And we won't belabor this point, but we do have to be aware of it because it is going to impact how we actually look at these structural components. What's the difference between a vector and a scalar quantity? Do you remember? What does a scalar have? Think about what you think of what are we looking at when we're looking at a scale?
Weight.
It's giving us a weight or a magnitude. Okay, so it's giving us a number. Sometimes our scalar will give us a direction also, right? If we talk about temperature, okay? This weekend it might get into negative degrees. I have two first graders at home and they just learned about minus temperatures this year and mind blown, okay? So, but we have to keep in mind that scalars can also have what the book calls a sense in its value. So think of positive or negative, okay? Where our vectors are different is our vectors add a direction.
Is that
Yep.
the line of action?
Yep, or a line of action. And so what we're talking about as we're looking at these, and we'll be looking at forces throughout the semester, how they're impacting, whether it's impacting a connection, whether it's impacting a beam, a truss, whatever it is that we may be looking at, but we'll have some sort of magnitude. Okay, and so we'll say 110 pounds, okay, and we'll want our magnitude to be representative of the force itself. So that if we have a 55-pound load, we want that to be about half, well not about half the length, half the length, okay, so that it's trying to push half as far, okay. Then we will have our line of action. Okay, so where this force is traveling along, and also its sense. Whether our force is moving along the arrow this way, or whether our force is moving along our arrow this way. Okay? Does that make sense? I know that a lot of the material in this chapter is fairly abstract, but if we get this down right now, it'll make the subsequent chapters much easier. Okay? So vector quantities, that's what we're going to be dealing with when we're talking about forces, when we're talking about analyzing our systems. And when we think about it from a construction standpoint, this makes a lot of sense for us, correct? Think about when we're dealing with, so last semester we went out to a couple sites. Think about when we were at the Encore. Remember the reinforced columns, post-tension decks. Okay, so if we aren't mindful of how the forces are traveling through that deck to our columns and how and how the columns are resisting those forces, we aren't going to be able to make sure that we're analyzing those columns appropriately. If we aren't analyzing them properly, we may not size them properly. If we don't size them properly, we may have failure. Okay? So we won't get into the complete components of design of them, but we'll look at how we analyze some of these things. Okay? These concepts are important to us from a terminology standpoint. We're not going to focus outside of the lab that we run next week. Spend a lot of time focusing our energy on these concepts. I think that once we get through the lab next week, I think these will become fairly easy for you. So let's take, I think concurrent is the easiest for us to visualize in our mind's eye. What does a concurrent system of forces mean? Forces are all coming to a point. Yep. So what's a real world application? What's an example of that? Yeah, a column interacting with a floor system, right? Because now we would have forces running along our wall, forces resisting our system, and then if you can imagine that I'm capable of drawing in 3 dimensions on a 2-dimensional structure, right? So we have forces coming into and out of the board. Okay, so we have multiple planes, but our forces are all coming to one point. Okay, so that's a concurrent system. When we're running our lab next week, everything that you'll be doing by nature of what we have to do analysis is concurrent. Okay, so we'll have to have everything come to one point. Okay. What about coplanar? What does coplanar mean to us?
Different forces with the same direction or same plane?
Yes, yeah, different forces, but we're operating in, I should do this in front of the board so that it's on the camera, right? So we would be talking about the forces in a wall, right? This could also be strictly the vertical forces in a column, okay? If we're ignoring any horizontally impacting forces on a column, then we would be talking about coplanar, okay? So all our forces acting in the same plane. And then what about parallel? What does parallel mean for us?
Two separate planes of force, like
Same direction, but
two walls, basically,
Yeah, exactly.
parallel to each other.
Yep. So they may not interact, right? So they may not come to the same point. Okay? But they operate in separate planes. What's a good example of that? Think about a structure. If our coplanar would be within the same wall, what could a good parallel system be?
Like a first and second floor.
Exactly. Yep. Very good. Very good. Multiple floors, right? We could also have the vertical components of resistance of a structural wall, and maybe we also need a shear wall that does take a little bit of vertical loading as well. So as long as we're only considering the vertical components of that construction, we would be investigating parallel forces.
so
Okay.
what would be concurrent? Like what's an example of,
An example of a concurrent force would be if we took a system of columns and decks.
okay,
Okay, so our decks are going to have first the force from their own weight, Okay, so they need to get that down to the ground. So they'll be pushing that along. They'll be pushing along any of their live load. So that will come along the deck to our column.
Okay.
Our column will be also providing resistance that's being pushed back up from the ground. And then if there are any floors above that construction, that will also be transmitting load. Okay? And we also have to keep in mind that we aren't building any 2D floors, right? I mean, hopefully not. Maybe we are at some point. It'd be very difficult to do anything with that construction. So we'll have load coming in the plane of the board, but we'll also have load coming in out of the board, right, from that floor, and possibly into the board, depending on how big our floor is. Okay? I know that the book gives you an example, but it's just a bunch of drawings in a Cartesian axis, and that's not, it's not always the most beneficial for us. So,
Nice that they use the actual components of a building.
yeah, and that's what, so in the lab next week, that's what you'll actually be doing. So you'll get a chance to analyze some different systems. We'll set them up in different configurations. A configuration where it's modeling this, configuration where it's modeling picking a crane. We could look at different things, setting up a column, although columns are going to be fairly easy. So we'll try a bunch of different orientations, and I think that will be more beneficial to you in understanding these concepts and help you set up for success anyway for the remainder of the semester. Okay, any questions to this point? We feel pretty good about this. Mostly nods in agreement, good? Okay, the next topic that they give you is static equilibrium. Okay, so we talked about this a little bit when we were talking about our acceleration equaling 0. So the first idea to think about is just equilibrium. And equilibrium can be good for us because it means that we don't have acceleration, but we may have constant velocity, right? Having constant velocity in our building would be bad as well. If our wall's moving along 10 feet per second, right? So equilibrium can be no motion or constant motion. Okay? Static equilibrium is the state where there is no motion. And what does static equilibrium mean for us? When we're looking at this point, what does it mean to that point to be in static equilibrium? What's happening to it?
It's constantly in the same space, right?
It's not changing its location in space.
Yeah.
Exactly. Regardless of how many forces we are applying to it, this point is staying in that in its place. Okay? Where is this important to us? Think about a steel structural frame. At what point, I mean, ideally everywhere, right? But where specifically from a design standpoint?
Where it meets the ground.
Where it meets the ground, very good. Okay? Where would be some other places?
Your bearing points for that?
Bearing points, yep. Okay? What do these points have in common in a steel structure? What do they have going on at those points?
Intersection?
They're intersecting and they're connecting, right? So our connection points, okay? So one of the biggest tools, or I shouldn't say biggest, most highest functioning tools for structural engineers in performing analysis and figuring out how to size a building. We'll get a chance to do a couple of these exercises. We won't go into as great of detail as we do from an engineering standpoint, is we will go through and look at all of the joints and see, will they be in static equilibrium? Do we have enough resistance to take on all of these loads? Okay? So that's a big component of what goes into structural engineering. Okay? That concept makes sense to everybody, what it is that we're after? Okay? And then hopefully not only our joints but also our members are also in static equilibrium. It'd be just as bad if our members are moving as it is for our joints. Okay? Does anybody need anything on the left side of the board still at this point? Okay. So the next thing that we want to talk about, I think once we get through this, once we get through this page, so we'll fill up this board one more time, and then we can actually get into some examples where we start wrapping our brains around what is actually going on in these systems in the field. So force components and combinations. Okay. So I have a couple things that we need to talk about. The first big one is a resultant. Okay. Does anybody remember what the resultant is when we're analyzing forces? So this is when we're analyzing multiple forces. Remember what we're looking for? Okay, that's fine. Remember that when we're talking about components and combinations, we can make any sort of setup that we want of forces. But what do we want to do? Let's say that we're setting up a crane, okay? And the crane has to be able to pull two different components. Using a crane isn't a very good example. We have 60 pounds running along our floor, and then because of wind resistance, we need a 75-pound load set into this angle. We'll assume that it's about 30 degrees. It looks like I'm fairly decent at drawing 30 degrees from horizontal. We want to make sure that once we set this system into place, the pull of this force won't take our joint out of equilibrium. Okay? So we need to figure out what type of resistance force should we put into place. Now, an easy way to do this is, well, let's just put a 60-pound load.
Try again.
Toss it.
Let's put a 60-pound load here and a 75-pound load here. That accomplishes the task, right? Equal force, opposite magnitude. Equal force, opposite magnitude. We have equilibrium. But what if we have, let's say we're putting in a steel structure. So now we have two more connections that we have to put into place. Wouldn't it be easier for our iron worker if we only had to put in one force, one source of resistance, one extra member? So if we look at, it's really awful that that doesn't work now. What if we took a projection of this force and a projection of this force, and we connect them? That represents the resultant of these two components. Okay? That is the combined effect of those two systems. Okay? So think about it if you're working out at the gym, right, and you're doing bicep curls, you may have one weight in each set of hands, right? But the combined effort of that work. Okay? Does that make sense? So that once we have our resultant, now we know I don't need those two connections. I can simply install one connection. Equal in magnitude to our resultant, but in the opposite direction. Okay? So the first part of your homework will be, and we'll work through an example here, but the first part of your homework will be determining some resultants. Okay? They give you some examples in the class, or in the book. So, the example that we'll look at is, say we have a system with a 50-pound force in the horizontal direction and a 100-pound force in the horizontal direction, okay? So again, how you solve these problems is you take a projection of your initial force. Whoops. Solid line, sorry. And we take a projection of this force, and where they intersect is where our resultant will run to. Okay? And there's a couple ways that we can determine what this force is, okay? If we draw them to scale, which I maybe did a decent job of, right? This is about twice the length of this, okay? If we know that this is 100, we can measure to here, use our additional scale, and determine that, okay? So we can measure it out with a ruler. We can also use a protractor and measure that angle. Okay? Why is it important to know the angle?
Or trigonometry.
Yeah, but think about it out in the real world.
The load.
We want to know where the load's going to transmit so that we know where to place our reaction, right? To resist that force.
So that'd be like those steel cables that hold up the poles.
Yeah.
That's how they know where to.
Yep. That's a very good real life example. Okay. Another thing that you could think of is, I mean, this could be, well, if we reverse the sense of it, if we had 50 pounds going down and we had 100 pounds going in, wouldn't that be the same as saying we're looking at the corner of a wall on a deck, right? Where we've got forces from the floor coming in, and then we're pushing forces down into the foundation. Okay. So I guess my recommendation for you when doing these problems, and there's, what does it end up being? It ends up being 6 of them. Okay. So I don't think it'll take you too long, but grab yourself a cheap protractor, use a ruler to make sure that you're scaling everything properly. And I'm fine for the purposes of these problems. I don't want us to spend a lot of time in getting lost in the rabbit hole of what resultants and equilibriums are. I just want to get through this topic so that we can get into the actual materials themselves. But if you use a ruler and protractor, okay, measure that length, measure your angle. Okay, that's what we'll be looking for those. So, does that make sense to everybody?
Are we doing the ones in the book?
Yep, it'll be, so the first set of problems will be problem set 1.3. So go back one page.
Pounds or force? It's the.
Where's that problem set 1.3?
Here's 1.3.
I'll have to look at where they are. Well, yeah, that's section. It's wherever the figure 1.3 is. I'll look it up and I'll post it for you anyway. So, another thing that we can look at is we may have structural assemblies where it may not be this easy. Our forces may not originate or terminate at the same point. Okay, but we may want to analyze them for whatever reason. So, say we have a system of forces like this, where we have, what does it look like, 70 pounds, and that's maybe 40 pounds? Okay? For the purposes of resolving them, you may back them off to a point where they're coming from the same origin point. And then you may put in okay? So I think the last two problems in the homework set will deal with this. Feel free to move them as long as you aren't changing where they are on their line of action. We can move our forces anywhere in that system, right? Does it seem believable to everybody? I'm not certain that everybody believes me, judging by the looks on your faces, which is fine. It's fine. I'd rather spend more time on it making sure everybody understands it than people just nodding and saying, yeah, yeah, I absolutely believe you.
Say it again, you can move.
We can move our forces anywhere we want to, as long as we aren't changing their line of action, right?
Yeah.
So if I take this 70-pound force, okay, so think about this as a deck, okay? We're on the 3rd floor of a building. Does the deck care if I'm pulling with 70 pounds here, or if I'm pulling with 70 pounds here? The deck doesn't care, right?
No.
Does the deck care if I'm pulling with 40 pounds here, or if I'm pulling with 40 pounds here?
Yes.
That it would, right? Because now I'm moving along, I'm moving this force in this direction, okay? But does the deck care if I'm pulling 40 pounds here?
No.
Or if I stand up on a ladder 4 feet taller and pull with that same 40 pounds?
No.
As long as I'm not changing my line of action, okay? So we can move these forces along the same line of action, okay? So look at the geometry and figure them out. Those would be the last two problems for the first section. And wrestle with them a little bit over the weekend. We can look at them in a little bit more detail on Tuesday. Tuesday's when we'll meet next. So we won't spend any more time on this outside of that set. But one of the things that we could look at is, what if we have a system of 4 forces? What if we have a system of 8 forces, 16 forces? Now we're actually dealing with what we deal with in design. The reason we're not spending a lot of time on this is we're not going to spend a lot of time designing these intricate forces. But the reason that we start with this type of system is it's fairly easy to resolve 2 forces, right? All we would need to do is, if we have 3 forces, 4 forces, 5 forces, 6 forces, okay? So let's look at a 4-force system. All we would need to do here is change colors here. This is where it's going to become hopefully not overly confusing what I'm doing, since my 3rd color doesn't work. But now what have we done? But yes, we've equaled these out, right? Have we solved the problem?
Isn't the sides?
But what do we now have? We have a system of 2 forces, right? So from here, I got to go back to black because my green isn't working, but oops. Lost that line of action. Looks like it's kind of poorly done along that same direction. So switch back to blue here. Okay? So what this tells us is, if we take this system of 4 forces acting in a whole bunch of directions, we can resolve it to 1 force and provide equilibrium to our entire system with just that guy. Okay?
So
that
you'd
make
only
sense to
need the
everybody?
one?
What's that?
You'd only need the one.
Yep.
So which one's only the one?
The left one.
The black?
The left.
Arrow.
flag.
So this is,
Well, he's blocking half of it.
that's our reaction for equilibrium. Okay?
I picture like Indiana Jones, right?
And we can do this next week in the lab.
Yeah.
Absolutely, absolutely. Yeah,
You get what I'm saying? Like I
I'm
picture
very willing to
Indiana
concede
Jones
to you.
on a teetering balance thing, and three people standing there, like you stand over there. Fix it.
Yeah, I'm definitely willing to concede. This is a very abstract concept, right? But keep in mind, what's going on out in a building? How many different forces are we dealing with? Hundreds.
Tons.
Almost infinite, right? I mean, if we really started breaking down our construction, we could be dealing with almost infinite forces. So the problem gets to be, when it comes back to the economics, don't we want to make it as easy as possible for ourselves out in the field? I don't want to have a connection resisting this force. I don't want to have a connection resisting this force. I don't want to have a connection resisting this force. On and on and on. If I can determine the impact of all these forces and get them into one force, I can say, Mr. Contractor, you need one connection able to resist X load, 400 pounds, at this angle, okay? So it makes our design easier. Well, it makes our design a little bit more challenging, but that's why we have computers, okay? But it makes it easier for our recommendations for how to size members. It makes it easier for recommendations as to how to place these situations, and it hopefully cuts down on the amount of installation time out in the field.
So is the
Okay.
resultant the weight of it? That do you just add the two forces, like you're 50 and 100 up in the corner there?
Well, that's
Would the
what I was
resultant
trying
be
to figure out.
150?
No, because like on some of these examples, it's,
I
well, it
gotcha.
should be 150, they got like 112 pounds this way. Like, how do they come up with that?
So so in sections 1.3,
Right here. If you go to section 1.4, there's the examples here, and there's 100 pounds going
Yeah.
like, horizontally, 50 pounds going vertically,
And
and
112.
then the resultant is
112 pounds. Yep. So this is where I would recommend in doing these problems, draw these with a ruler. Okay? So if you draw this,
Oh, is it a ratio?
yep. So if you draw this at 4 inches, and if you draw this at 2 inches,
That might be.
this will be 4 1/8 inch,
Yeah.
Okay,
right?
So it's a
Okay.
ratio of the 150.
right on.
Yep. Now, how else could we do this?
Tracking glue.
What's that?
Well, trigonometry.
We can solve it with trigonometry,
Yeah.
right?
Yeah.
Okay? So we can figure out what this angle is. And how we can figure out this angle is, we know what this magnitude is, right?
Well, we know it's a right.
We know it's 50 pounds,
50 pounds, so we know it's 2 inches.
Yep.
okay? So how do we determine what this angle is?
Pythagorean theorem.
Yeah, you could, yep, absolutely,
Use
yeah.
that, but
That's a
you
good
could
point.
also-
You could solve that with Pythagorean theorem too.
Some old hippie got another hippie.
Square those, take the square root of the sum, okay? But would you rather measure it with a ruler?
Yeah.
I'll leave it up to you. If you want to do the math,
Using the ruler and
you can do the
protractor.
math. If you want to use a ruler and protractor, use a ruler and protractor, but just draw it to scale, okay? So,
I think we need like a refresher and trig.
don't you worry. Guess what we're going to be doing this semester? We'll do a refresher and trig.
All right.
So, okay, so we talked about the equilibriant. The last thing that we should look at, they talk about force polygon. Okay, so don't worry about the force polygon from the standpoint of testing or homework. I just want to talk about it conceptually so that we can tie it together to the static equilibrium. And this is the example that they use in the book is, see how closely I can recreate it. Say we have our system. Okay. So, if we were to break apart all these forces and put them into a polygon, what would we need to have to be at equilibrium? Can that polygon have any open sides?
No.
Or does it need to be a closed loop?
Well, wouldn't there be
Be
one open
closed.
side that you're gonna put the?
Yes, very good point. This
The
currently
action-
will have one open side, right? Because if we pull on this point in all these different directions, we may have motion, okay? And so what we want to do is figure out what is it that we need to do to resist this from moving, okay? So if we draw our system, roughly to scale, hopefully to, I'm fairly good at recreating this. And then let's maybe do that guy then too.
Where's
And then we'll do that guy. Okay, so now we have our four forces, right? To close our loop, we would need that guy. I messed up the magnitude a little bit, and the line of action. All right, but this, if we drew it correctly, should equal this. Okay? So that's the whole point of when they're talking about force polygons and Bose notation. That's what they're getting after with this. From the standpoint of completing your homework, I'm not going to give you anything where I say break apart these arrows and make a polygon. Okay, we don't need to.
So you're just drawing,
You're just blowing apart all your loads, right? So saying they're no longer at one point. Got one guy here. Got one guy here. One guy here. One guy here. Okay. Then how we join them. That should have. Had I taken more care with drawing my system,
yeah.
right? The line of action and the magnitude of the force to close the polygon will be identical to the resultant that you get using this system.
So what I'm trying to see is like that you just drew,
Yep.
is that supposed to be the dotted lines over there? Am I,
This,
yeah. How
so
did you?
what I drew here is these forces,
Okay,
which remember, this was the original
yep, I see that one.
forces, okay? So over here, we went about it a different way. Over here, we reduced our system to two forces, then we reduced it to one force to get our resultant.
Okay,
Over here, we said, well, rather than reduce our forces, let's blow them apart and draw them individually to close a loop. Once we close the loop,
so if that had one more force, would it be closed? You wouldn't need the blue one?
yes, but then it wouldn't be the same as this, right?
Right, yeah,
Yep.
okay.
So, I get what you're after, but
Yeah.
you can only use this as separate analysis if you're looking
If
at the
you're already-
same system,
Okay.
okay? And so what we're saying is that up until we get to this point, we haven't resolved. All we have is what these guys are, okay? Once we close it up, now we know what our resultant is, okay? And keep in mind, typically speaking, the purpose of determining the resultant isn't so that we know how all those forces are interacting, so that we can figure out how to keep our system in static equilibrium, okay?
It's not gonna
It's okay?
be, 'cause
The homework that you have is gonna be like this, okay? So you don't need to, you're not gonna need to do force polygons, okay? We're not gonna, for the purpose of this class, I don't wanna dive into and run statics on a whole bunch of, we're not gonna calculate this for 4 different weeks. We're gonna get into looking at concrete structures, looking at wood structures, looking at steel structures. How do we actually keep this in mind when these things are being designed, to figure out how to size the elements, okay? That's where we're really after, okay? So, this is all the stuff that the computers are doing,
Okay,
okay?
you ruined my weekend. The start of my weekend. But blowing my mind.
That's fine. Just so you know, I had a college professor who ruined my semester doing this stuff, okay? We would do this for an hour and a half, 3 days a week, for an entire semester.
I'm just
Yeah.
trying to correct.
No, it's fine, it's fine. And that's the purpose of this class. I want you guys to get your homework on Thursday. You can wrestle with it over the weekend. We'll come back and we'll look at it on Tuesday mornings, okay? So, I think that once we get past the first couple chapters, and once we start getting into looking at connections and looking at how we're actually sizing things, you guys will pick up a lot of steam at that point. And you'll
Yeah,
really
I think
you'll really
it's
get
just so
grooving
left
with it.
field right now that it's hard to swallow.
Running this lab will help you too next week as well, okay? Okay, so that covers all the, oh no, sorry, we still have moments. It's okay though.
Let me kick you in.
No, moments are good. Moments are a little bit easier. Do we remember what a moment is?
Yes.
Outside of an instance in time, right? A moment is certainly an instance in time. But from the physics standpoint, what does a moment do? Think about a beam, okay? So we've got a beam coming out of a connection, and we put a weight on the end. What is the beam going to try and do? What does the beam want to do? It wants to bend, right? So what's happening at the connection?
It's bending or
The connection's trying to rotate, right? And so, if we're able to keep the connection in point, it's not gonna rotate, but what happens if our connection rotates?
snaps.
We could snap our beam, right? We could have a beam fall and probably kill someone, okay? So, we typically wanna resist bending moments, okay? So a moment is the tendency of a force to, oh goodness, sorry, it's awful. Of a force to cause rotation about a point. Okay? How do we calculate a moment?
With
Distance
mass,
times force.
distance.
Distance times force, right?
Yeah.
Okay. So what we could have is, let's say that we have a 100-pound force, and it's moving in the plane of the wall. Okay? If we have, oops,
Is distance talking about the length of the wall then? Because it wouldn't be moving.
no, it'd be this distance. So it's whatever your distance away from the point. It's going to depend, okay? So think about a bridge deck.
Okay.
What do we put underneath bridge decks, over the columns? So we have our columns or our piers. What do you always see?
Girders.
You have some sort of girders, but you have a pin, right?
Oh, yeah.
If we're over a pier, what do we have along one edge? Or sorry, we don't have pins over the piers. We have rollers over the pins, right? We have pins along one side of the bank. Why do we do that? What happened if we pinned a bridge deck in multiple locations?
Have multiple points.
Yep. As it's expanding and contracting, if we're providing resistance at a bunch of points, couldn't we crack the bridge? Right? We could involuntarily fail it. So what we'll actually do is our bridge deck will be secured. It's a terribly drawn bridge deck, sorry. So we're secured here, right? So that pins our deck into place. Can't go anywhere. The roller supports it, but as in the summertime, as the material expands, our roller will rotate slightly, right? This is obviously exaggerated for a comedic effect, right?
Right.
If our roller rolled that much, it would roll right off the pier, right? But it allows it to move along with that expansion. Just as it does as wintertime comes along and that bridge tightens back up, our roller can move back into place and rotate back along with it, okay?
So that movement is the distance?
No, not quite, sorry.
Okay.
Sorry, I was getting back to just defining what our reactions are. Now, what do we put on our bridges? Cars and trucks, right? Our cars and trucks have load. Okay? So we have some sort of truck. It weighs 2 tons. Okay? And we're going to assume, as we'll do for most of the homework that we do in this class, we're going to reduce things to a much simpler way of doing things, whether we're looking at point loads. We'll look at some uniformly distributed loads as well, but let's consider our truck, instead of being 53 feet long and applying that 2-ton load, well, it wouldn't be applying 2 tons if it's 53 feet long, but so we've got, we'll say 20 feet, right? Instead of distributing that over the 20 feet, we'll just say it's 2 tons being applied at this point, okay? So you would determine how far away are you from your reaction. This is your distance
Okay,
that you use,
okay,
okay?
that makes more sense.
Here's your D, here is your F. The other thing that we have to keep in mind with our moment is we want to make sure that we're aware of what type of rotation we're exhibiting, okay? And the easiest way to visualize it when you're looking at it, because it's never truly a 2-dimensional thing, right? There's always going to be a little bit of torsion in there. But the easiest way to envision what is going on with that rotation is take your hand, okay, and with your thumb pointing straight out from the plane that you're looking at, if you can curl around that force and rotate, that's the direction of your moment. Okay? So does everybody see that if we're looking at it from this reaction point, this force is going to make a moment curling in this direction?
Yep.
If we look at it from here, though,
That roller will be going on to going this
it's going to want to take our roller and rotate it back towards the truck.
counterclockwise.
Yep. Okay? Does that make sense for everybody? Decent-ish tool to help you visualize it. I don't know why they don't include it in here. It's in every statics book that engineers take. It's one of the first things that we talk about is how to visualize the moment, because it is a challenging concept, at least to think about. Another way to look at it is, say we have 3 feet here, say we also have a point A here, and that's 5 feet away, okay? So if we look at our 100-pound force, and what it's trying to do to point B, what is the moment going to look like? Is it going to curl clockwise, or is it going to curl counterclockwise?
Clockwise.
It's going to want to curl it this way, right? Well, what about with A? What is it, A. What is it going to want to try and do to A? Is it going to try and curl it clockwise, or is it going to try and curl it counterclockwise?
Counterclockwise.
Keep in mind, we can move this force anywhere along that line of action, right? So if I have this force here, what is it going to do? It's going to curl this way, right? Okay, so
So is a moment a number, since it's force times this distance,
what is its units?
can you, yeah, so if that was 2 tons And I don't,
4
10
feet.
4 feet, so
What are our units?
would it be,
4 feet.
Pound foot, okay? Our units for moments are always pound foot,
okay,
but it's okay. I know this isn't something that we measure out in the field, right? How do you measure a pound foot?
so 1,000
Feet a pound.
feet a pound,
1,000
or pounds a feet.
Yeah.
What's that?
That'd be 1,000 pounds a feet. 4 feet, 4,000 pounds.
It's not pounds per foot, it's pound foots, okay?
Okay,
So your equation is going to be moment equals,
Be 16,000 pound foot.
yeah, 4,000 pounds times 4 foot. Okay? And it's fine that this isn't a real world thing, right? We can't go out and measure pound feet. We can measure pounds and we can measure feet, right? We use moments to help us determine static equilibrium. Okay?
So it'd be 16,000 or 1,600?
16,000.
missing a zero.
4,000, yeah, missing a zero, sorry. 16,000, yes.
Okay.
Okay? And then the last thing that we have, and then we will look at some, then we'll look at some examples. That's what we'll close out. How much time do we have? I should have looked at that. Oh, we don't have time to look at examples. The last thing to keep in mind for equilibrium is we have to satisfy 3 cases. Okay? So, the sum of all our forces in the x direction must equal 0. The sum of all our forces in the y direction have to equal 0. And all our rotations have to equal 0. Okay? Does it make sense why those 3 conditions have to be met? Well, they don't have to be met, but what happens if we don't meet all of these?
And you don't have the equilibrium.
Well, we don't have static equilibrium.
Yeah.
Our point is moving. Okay? Now, if we were looking at, I don't know, if we're looking at pacemakers, if we're looking at things that have electrical components, yes, we want things accelerating, right? That's how they function. The construction world, yes, we want our cranes moving, yes, we want our equipment moving, but our final product, we typically don't want moving, right? Architectural features, things of that nature, but when we're talking about structures, we want those guys, okay? Oh no, we go to 11:30, don't we? Okay, perfect. It's only 11 o'clock. So then, yeah, we have time to walk through a couple examples that will help you with the homework that you have. And we'll spend time taking any questions that you have on Tuesday before we get into the lab as well. We probably won't have time to go into a whole lot of detail on the lab, but so we looked at that guy. So let's look at a moment. Okay, so consider a beam, and hopefully when I get done drawing this, there's something that screams out to you that we're going to have a problem. Would everybody be comfortable traveling on this?
No.
No? Why not?
Tip.
It's gonna tip, right? Okay? But the sum of all our forces in the x direction equals 0? Okay?